thank you very much. All right, and then we saw two great examples of workbook. Supriya will be sending that. So today I will record this session also, and then it will come to you. Yesterday, I think probably today late morning I was doing it. So what is that? Two great workbooks I shared with you. Fisher Iris data and Cleveland Hot Studies data. 5-class model, multinomial model. So do you know how to do multinomial model in a simple way? Use the forest. Right? There are many ways to do that, but forest is better, simpler, easy for it. Okay. And also I showed you those are the things, right? Fisher Iris data and Cleveland study data, right? Those are things. Let's do today SVM, support vector machine, and their applications. Okay. Again, there is some level of mathematics there. I'm not going to talk too much about mathematics. Let's go. Jump in. Okay. So this particular visualization you already saw. You remember that this particular visualization, I shared with you. So the output of that is that it is really the Iris Fisher data, Fisher Iris data. Are you able to see this one, everybody?
Yes, sir.
Okay, I'll make it bigger if you want. So there are three flowers: Setosa, versicolor, and virginica, and they are colored differently. This is something I have given you the codes for you. And then this is the sepal, and you all know what is meant by sepal and petal. For both of that length and width. So 4 variables are there. Okay. I take 3 at a time to show it to you, okay, because 4 variable is harder to show any other way. Okay? And if I rotate, if this is the same picture, after I plot this, if I rotate in a particular angle, look at this one, SL came here. Now it is here SW, right? S instead of sepal width, I brought sepal length here. But if in that view, you can see that there is a linear line. Just linear line means just a line. Just a line that separates these two perfectly, these two. And these two, this line is pretty close. Okay? There are some overlapping points. There is nothing you can do about it, but this is the best line. So a line can do your tricks. Just a line can separate out. That's what this means, predicting. That means to the left of this line, you are saying it is Setosa. To the right of this line is either this versicolor or virginica. But then if you combine that with this information, to the left of this line and to the right of this line is versicolor and remaining is virginica. That is the predictive rules. Everybody got it? So how do we find this line? That is the question we are talking about. So this is another way of looking at it. Rotated to see the regression plane. This is a line. It can also, this is really, even though I call it as a line, it's a plane. What is the difference between a line and a plane? It is just a sheet.
Line and 3-dimensional line in 3 dimensions is a plane.
Yes, it becomes like a plane, right? That means a sheet of paper like that. Okay. It is the same thing. I'm rotating it to show it. No, this one is not this. This one is not this line. This is a separator line. But this is a regression line. What is the difference between a regression plane? What is the difference between a regression plane and a separator? Separator is basically, it separates these classes. But regression is, it is the best that fits the particular class. It is the best that fits this data. Are you with me? Fits this data means it will be going through the middle, right? The best middle sheet, middle plane. Are you with me? This is not a separator. This is a regression. That's why this is called a regression, right? This is not a separator. This is a regression. See, if I rotate more and more, you can see it. This is to rotate it to see that it's the fitting line. This is the distance between this one and this one. This is the distance between this and this is this line, and so on. Like that. Here, I am showing you the regression plane for the versicolor, and this is also a plane. You can see that by rotating it. That is the best fitting plane for this data. These are regression planes. These are we can do all these things in the workbook I gave you, right? Did you see that workbook by any chance? Have you had a chance to explore You remember that workbook, Goshen?
We did this.
PA2. When I introduced PA2, I gave you that, right? What is that, Rajan?
Ma'am has sent this to,
What is that?
Ma'am has sent this two files, sir.
I cannot hear you when you speak. Can you?
Ma'am has sent
Oh,
this
ma'am
two
has
files,
sent.
sir. So, yeah.
Yes, ma'am has sent. That's right. But my question is that are you folks play with this one? It should get you should be curious about it, right?
Yes, sir. Yes,
Okay.
sir. I go through a little bit.
Thank you. How about Soumya?
I did not go through it actually.
Everybody has to go through because this is if you want to show multidimensional rotation, you will impress your interviewer. You can rotate the data in 3 dimensions, show them means. For most of the applied problem in 3 dimension, even if you have a huge dimensional data, you can reduce it to PCA, top 3 PCAs. You remember that? Top 2 PCAs, you can just show them. People can see the results. And if you, by the way, what is biplot? Everybody knows that? Rajan, what is biplot?
No.
You know it, Gaushali?
Yes, sir.
Okay, so I'll come to you. Sharanya? Okay, you know it. Rajan, Shaktiveer, Rakesh. Rajan knows. Good. Who wants to jump in to say, what is it biplot? It could be a good interview question. What is biplot?
A plot which combines the first.
Huh?
We can plot two principal components.
That's it. 2 principal components. First top 2 principal components is your biplot. Top, write it down today. If you don't know the simple definition, top 2 principal components and how the data points fall on that top 2 principal components is your biplot. So you know the definition. What is meant by biplot? Tell me the definition in your own word, which I didn't tell you so far. What is meant by triplot? That means 3-dimensional plot. What is that? So you can say that answer right away. What is it? Sharanya, Soumya, Rajan. I think Rakesh, you know it, right? Anybody want to jump in? Extend the definition of biplot. That's all you have to do. Extend it. Try.
You can visualize top 3 principal components.
Rakesh said it. I was explaining, somebody else will jump in. Okay. Gaushali, you're good? Instead of 2 PCA, take 3 PCA. But if you, so what I'm saying, most of the visualization, you can show it in 3 dimension. T-SNE, that's one of the visualization. T-SNE is basically that triplot. It is just a triplot using top 3 principal components. But we use some transformations, so that it is, the data is visualized in a certain way. T-SNE, write it down. T-S-N-E. T-S-N-E. It is basically 3-dimensional top 3 principal components based plot. Please write it down, that sentence. People might ask you, what is T-SNE?
Could you spell that? What is that? T?
T, letter T, dash S-N-E. Usually S-N-E is uppercase. Okay. All right. Now, for all these things, you can use it. That's my point. Right? Let's keep going. So the fundamental problem is I am not talking about regression, multidimensional regression planes and so on. I'm talking about separator in multidimensional space. Multidimensional means many dimensional data space, right? Everybody's good. Separate. How to find the separator? This problem has been solved by statisticians a long time back with the what is called linear discriminant function. They used to call it a linear discriminant function. But they stopped there. they used normal distribution, linear discriminant function. They tried nonlinear discriminant function and so on. But what people did, SVM people did. SVM refers to, please write down, support vector machine. Support vector machine. So SVM people, what they did was they proved that because the data may not be linearly separable. The data may not be linearly separable. For example, I'll show you. If you have data like this one, everybody look at this one. Is it linearly separable? In other words, can a line or can a plane separate this? Impossible, isn't it? I'm talking about this non-linear decision boundary here. This is not linearly separable. And that is what these data types are all here. But take a look at this one. Take a look at this picture. What we are saying is that now, if I can pad the variables, predictor variables, if we pad the predictor variable, that means add. Pad means padding, so that it is, the full, in addition to the existing one. If you add the existing predictor variable with certain new variable, which are transformations of the original variables, then the two-dimensional data will become represented like this in three-dimensional space. Are you with me? In that space, you can see that all the red points are lifted. There is a transformation. That's the beauty of human mind. We figured that out. There is a transformation, we can figure that out. That will lift all the red points to up and all the blue points below. So a sheet will separate it out. A linear line or linear plane will separate it out. Are you with me? So what is the benefit of that statement? Very powerful statement. You don't worry about all the non-linear, fluctuating planes and all to separate it out. No, just linear line and linear plane is good enough. That's extremely powerful. And such transformations are called kernel transformations. Such transformations are called kernel transformations. And that is what in a two-dimensional also it is like this. This is I put it in a three-dimensional, but two-dimensional. This is hard to separate it out in linear line. Sharanya, this is also hard to separate it out in linear. Okay. So what it is, we find a kernel function phi. It's a transformation, right? That will transform all these points into this. This is phi1, phi x1, phi x2 here. But when you transform it like that, it becomes separable perfectly by a linear line. Such transformations are called, please recall that name. Such transformations are called kernel transformations. Okay. Kernel, so please write it down. This is an interview question. What is meant by kernel transformation?
So what padding values do you add to?
I haven't come to you now. I am only talking to you in graphical form to you. I will show you that later. Okay. What kind of functions are these? I will show it to you later. I'm trying to get your attention right now that the possibility of just the linear line, just the linear plane is good enough to separate classes. To separate classes. Are you with me? And such transformations are kernel transformations. So let's go back to what I wanted to tell you. So fundamental problem is if I can find out, basically if I can find out the separated, linear separated, I solve the problem. That's my point. I don't have to worry about non-linearity, all those things. Immediately your mind will think, if you are like me, you'll say, oh yeah, you can talk about all these linearity, these are all simplified, these are all not, all the practical problems are not solvable. This is sometimes I think crazy, right? And I think a lot of us are like that. But the point is, I settled that issue. At least I told you that don't worry about it. We have solved that problem also. Everything is linearly separable. In fact, this is a good statement. All classification problems are linearly separable. That's what the fundamental point of SVM. all classification problems are solvable using linear separators. That's the end of the story. That's what your problem is. But how we have to establish a lot of things to come to that one great statement. But most fundamental to that is just show me how it is linearly separable even in a simpler case. That's the first one, right? That's what this example is. In other words, I have these black points here and then these white points here, right? Bounded by black color. So, if you want to separate out these two, H1, does it separate out? No, right? It doesn't separate out. How about H2? Yes or no? Charnia? I can't.
Yes,
Yes, sir.
somewhat.
Yes, sir.
Yes, it separates out.
Yes.
It does.
Yeah.
How about the H3?
Yes.
Yes. So H1 doesn't separate out. H2 does separate out, and H3 does separate out. But why? Which one is better? Obviously, H1 is not good. H2 does its job. What's the problem? It solves its problem, right? It does its job. H3, of course,
H3
it also
separates
solves
both.
the problem. The question is it better to have H2 or H3? Somebody
H3 is better.
H3 is better. Raja says H3 is better. We'll come to that point. Anybody else says H3 is better? I can't hear you, Sharon. I cannot hear it. But anyway,
H2
everybody.
also better, sir.
I'm sorry?
H2 also better.
H2 also better. Okay, so two views we have here. Why do you think H2 is better? Also better. In other words, both are equal. That's what you're saying. Okay? Why do you say that, Goshen? You got some reason. Just share.
H2 separates the black dots and then white dots. It's in a straight way.
That is correct. That is correct. Both H2 and H3 separates. The question is, which is better? And you said both are equally better. Of course, both are equally better for separation purposes. Absolutely, both are equal. If separation is all what I care, both are equally good. But is that the best way to characterize it that will be applicable effectively for all problems? That is the extension I want to think, which you may not know now, but I'll come to that. Raja, you said H3 is better.
Yeah, because I was thinking, at least in terms of the distance from this line or plane, in respect to the two data sets that we are having, which would be the best possible answer, right? That's how I was thinking.
Very good, very good. So he says, look, this distance, that's what this blue dotted line means. This distance is written, I concocted this in a way that, all these things are expressible. This distance is, same as this. You are right, perfect, right? So all these points are equidistant from this line. That's what Raja said, right? It's a right statement. How about this one? This is not equidistant, you think, H2, Raja? That is why I put this one. I didn't highlight this point, this line. Are you able to see this line? Maybe I should make it bigger and thicker. This line.
Yeah, I can see that line. H2 you're talking about.
Yeah.
Or?
So the distance between this point and this is the minimum distance between this point and this line, and also this point and this also visually looks equal. Correct? So now, is there any other reason one can find that out? Well, one can articulate why this is better. H3 is better. In H3 is the better. That is the pathway we are going to take. Rakesh, do you see what I'm saying? What can we say about which, can we say anything additional? So what we are talking about is something called maximum margin. In addition to equidistance, we want to talk about something called maximum margin. The margin is the whole collection of points, and this whole collection of points. The maximum margin is happening in this area, not between this and this, because this the points, these are the critical points. I'm going to call that now, from now on, these are the critical point that is defining the maximum margin, and that is a special term for that is called the support vector. The whole margin between the distance, the whole marginal distance between this collection of black points and white points is determined by only these two vectors. Every point is a vector. Remember that in multidimensional space, every point is a vector. So they are determined wholly by these two vectors. They are called support vectors, not this vector. In other words, the distance, the whole margin between this and this is not determined by this and this. It is determined by some points, but not this one, and it turns out to be this point and this point. Do you see that one? What I'm talking about, a maximum margin between these collection of points, Rajan? Maximum margin. Okay, go ahead. Rakesh, do you understand the maximum margins, right?
So the maximum margin is the maximum distance from the line.
The maximum margin, okay. The maximum margin is maximum possible distance. You are right. Maximizing the distance. This is not maximum distance. Where the maximum margin is the place where the maximum distance occurs between the two collection of points. Everybody got it? So from that point, we need to fix two things. We need to fix two things, right? Two things. One is where, what the maximum margin is, and what are those points, the support points, support vector points that are actually helping us define the maximum margin. And using that support vector points, we find the separator. That's a problem solving method, strategy. Everybody's good? So two concepts are coming. One is you have to find out the maximum margin, for this, for these points, collection of points, classes, and then you find out the line that is equidistance for that maximum margin area, which are determined by some special vectors, called support vectors. Everybody's good so far? That is our strategy, analytical strategy, algorithmic strategy, not even analytics, algorithmic strategy. Because the whole collection of support vectors is an algorithmic approach. That algorithmic approach is done by this. Are you with me, Samya? Shaktivel, Goshali, everybody's good? So,
Yes, sir. Yes.
Very good. So, that is our purpose, to find. So, the thing is, there are a couple of things going on here. We need to find out what are the support vectors. That's a problem, right?
So we're concluding that H3 is better, no, sir?
Yeah, oh, yes, of course. Yes. H3 is better. Because that is the one that is addressing the maximum margin. Okay? And that maximum margin is defined by support vectors, key vectors. And in this case, two vectors is good enough to solve the problem. You can have billions of points, black points, and billions of white points. It doesn't matter. It takes only two support vectors. Do you see this one? There's some beauty going on here. The whole science of separator is found just using only 2 points. Are you with me? Isn't it exciting? It's amazing. If we can solve that kind of solution, if we can create that kind of solution, it's unbelievable, right? What we are saying, you can have billions and billions of points on both sides. Doesn't matter. You just need only 2 points to determine the separator, and you can solve that using maximum margin definition, and you have solved the problem. And you keep adding additional points, and every time it is always falling beyond these support vectors. You go solve the problem. Continue to solve the problem. I understand in practice it may not be so clearly separable like this, but we'll come to that. But there is a beauty here. That's why, for example, in some application, where you need to solve the problem with minimal points, note it down. This is an amazing strategy. If you have only minimal points to solve, small number of points, and if the points fall to the left and right of these support vectors, you can still find a great solution. Do you understand what I'm saying? So with minimal points, you can solve this with support vector machine. This is this method of the engine that cranks out this maximum margin equidistant line. Please write it down. Maximum margin equidistant separator. That is what support vector machine is. Maximum margin equidistant separator. Supported by or developed using special vector called support vectors. Created by using some special data points called support vectors.
Separated by using
some special data points called support vectors. So that is our the strategy. That's our approach here, and I think it's amazing, right? There are a couple of points, amazing points here are that just 2 points is good enough. It doesn't matter billions, it doesn't matter at all. That's one thing. The second one is it's all about linearity. Something about linearity. If you can solve everything by linear functions, that's amazing too, because it's all just about linear. It doesn't matter how complex the data is, isn't it? Amazing. Okay, so let's solve the problem. So here is a little bit of mathematics here. I kind of would like to share with you, but let's see, huh? Yeah. And these are all more and more, more and more stuff. You can read these things. Having understood what I said, you can read these things. So here again, another way of representing the same thing. But all I expressed, it's all here. Okay. So instead of saying that all the x points are, all the x points and y points are categorized either -1 or +1. Again, in some different notations we will use, and this is another way, right? How many support vectors are here? Somebody jump in quick. How many?
looks like 7
There
or
are
8.
3 actually.
Who said 3?
Raja.
Raja said 3.
Yeah.
Somebody said 7. Okay. Any other number? Any other number? No. Shaktivel, Goshali, Charanya. How many support vectors are there? Huh?
3, sir. 3.
3. Okay. So any other number you have? Anybody wants to just jump in? So rest of you all thinking 1, 7 remaining as 3. Is that what it is, Soumya? What do you think?
Yeah, even I will go by 3.
3. You will go with
3.
3. Rakesh?
Sir, am I audible, sir?
Huh?
2, sir.
2. Who said that? Rakesh?
Rakesh.
Rakesh said 2. Okay. Anybody else?
Sir, am I audible?
3, sir.
3, 2, 3, 7. Who said 7? Rajan said 7. Okay. Why did you say 7? Count it for me. Which are the 7 here?
No, I mean, I feel that there are 7 lines that can be possibly drawn between these two.
No. I asked only support vectors. I didn't ask for the separators. How many separators? I didn't say. That's a good point. We have to learn all this terminology, right? Separators. I'm not talking about separators. Only support vectors. Yeah, is the question clear to you, everybody? Did Rajan clear to you for you? Okay. So how many support vectors are there?
Only one, then the case.
Only one. Why do you say only one? Which one is that? Support vector.
The red line. Sorry, support vectors 2. Sorry.
2. Wait, which are the 2?
The 2 ends of the dotted lines. That dotted lines.
You mean this 2?
Yeah.
Or this 2?
The line, the dotted lines.
Both are the dotted line. You are still talking about, this is what is called basically the end of gutter. It's called end of gutter. This is you can call this as a gutter. So these are the ends, okay, which are basically connecting the support vectors, okay. So yes, you support vector refers to the data points. Remember that, okay? They are not lines. Separator is the line or the plane. Virtually, you said 3. Great. It is 3. The answer is 3. Support vectors are again the ones that are the basis that determines the equidistant line. What is the equidistant line here? Can somebody tell me? It has a specific color.
Distance between
Red one.
distance between the two classes.
Red.
The
Red
distance
one.
between the two.
Yeah, that is the equidistance. I know that is the reason why I made it as a red color. Okay, or maybe I copied it. I don't even remember. Copied it from somewhere. Okay, so red is the equidistance line. That is the separator. That is supported by these 3 vectors. These 3 vectors. The star vector. These 2 vectors here. Right. So this is another example. Just to quiz in your brain. The concepts. So it comes down to. Okay, let's continue to do this one. What is this one? Now it is getting complicated. This is more real, right? There are points on this side, there are points on that side, and so on. So it's a little bit difficult also. Why this is not a support vector? Can somebody tell me? This cannot be a support, right? Because if I do that support vector, this side, if I go to this as a support vector, this is it becomes part of this red almost, right? Yeah, not almost, it is part of the red. In a linearly separable thinking. Enna Raja, are you with me? This point cannot be support vector, right?
Yeah. That was also. I mean, I was thinking about that actually initially in the first slide, because we can't expect the whole set of data that we have on one side, right, to be on one side only, right? It can be. It can be anywhere actually. So, and we are talking about we can actually try to linearly divide it into 2. How do we then take those outliers actually, right?
Yeah.
That was.
So that's a case 2. Yeah, that's a case 2. Now I come to the case 2 now, right? That's what we are talking now. What if the data is not linearly separable? There are outliers or noisy measurements, that makes it, not linearly separable. So obviously it is going to become non-linearly separable. It is non-linearly separable. In other words, if I go through like this, like this, like this, and like this, and like this, right? Everybody? That is non-linearly separable. So how do we understand the separate? It's not easy to determine visually, right? Because you have to think about a lot of other things coming into play. Constraint optimization is coming. Okay. So, but it turns out that this is the line that is the best separator for this data. Visually only I'm talking to. I'm coming to the algebra and computations. Just stay put there. And how it happens is that, so we, in optimization, what is the optimization we have? That I have to show it to you now. So let me first show you the optimization before I come to this nonlinear separator, please. Okay, the optimizing function. So the optimizing function is little bit of mathematics. I pushed it to the bottom here. 1 second. Okay. This is a little bit of mathematics I want you to understand. Are you able to see this one? Distance between a point and a line. So I have a point here P, and I have a line. The distance between a point and a line is basically the perpendicular line. Perpendicular line could be only one. You remember that, right? The perpendicular. That is what the distance is. Wherever it falls, if I drop, let's say, I drop. This is some kind of a floor, right? And this is the first floor. And somewhere on the first floor, I go and then I drop the pendulum, right? Something like a pendulum weight. That one weight. Wherever it touches, that is the distance. It won't fall here, right? Because of gravity, it won't fall here. Wherever it will touch exactly perpendicular, and that is the distance. So how do we find the distance? Well, this is very simple, high school mathematics, maybe a high school advanced mathematics. I don't know. High school mathematics. I'm not going to spend a lot of time here. It is written here nicely. You can read it. But it turns out the distance between this point and a line should depend on this line equation. This is the line equation, okay? Ax plus by is equal to 0. That is the line equation, because it can be written as y is equal to mx plus c. Y is equal to mx plus b. I can derive from here, right? So it should depend on the values of a, b, c, and it should depend on x1 and y1. That's all it should be, because there is no other information here, isn't it? There is no other information I have. I have the point, I have the equation. The distance has to be written somehow. We're only using this information, a, b, c, and this point x1 and y1. And that is this formula. Everybody? That is this formula. So if I give you any point and a line, this is what we are going to be the equidistant line. Let's say we are going to find that out, right? So, but that formula, any point, this is a support vector. I have the support vector point, and I can find, the distance between that support vector point and the equidistant line. Right now, we don't know what the coefficients of A, B, C is, but that algebraically is this. Everybody gets the understanding what I'm saying? Rakesh, Rajesh, Gausha, Charanya, Soumya, Raja.
Yes, sir.
This is the formula. What is this formula does? You give a point, and that is going to be the support vector point. Okay, you give a point, then you want to find a line, some line. Don't even go to equidistant right now. If you want to find some line, and what is the distance between those two? Just use this formula, you get it. You can't find the answer for the distance. But that should happen equidistant on both sides. So it should be equal on both sides. Two equations and two unknowns. That's another way of saying it, actually. Two equations, two unknowns. Okay. And we can solve the problem. And once you know the two equations, two unknowns, C is this. So there are three parameters, but we can solve that. C is the function of all these values. That's one way of looking at it. But we will use, optimization method, minimization method, maximization method. That's called optimization method, because mathematically, we can do that easily. And this is logically I am telling all this things, right? Mathematically, what is that we are going to do to find that? If I show you that equation, you should be fine. Everybody agrees? What is the equation you have to optimize, minimize, or maximize? Well, if I give an equation, you can minimize and maximize. That right? Everybody knows that. Use the first derivative, second derivative, isn't it? Everybody knows that? Rajan sir? Rajan sir? Don't know? Oh. What did you do undergraduate degree? I'm pretty sure you know it. If so, maybe you forgot. Tell me.
Biological sciences.
Biological sciences. What about you did postgraduate?
Basic medicine.
Basic medicine. My goodness. Oh, gee, I understand now why you have sometimes you kind of worry about all these things. So I have a slide in PA1. Okay. I show how to find the minimum of a quadratic function, which is a U function. That is Venkatachalapati Nama, U. That u function minimum is attained at the bottom, right? How do we find that kind of function? That kind of graphical form. I have one slide there. Because I know we still have to recall these things, so I provide these kinds of little details. Okay. Can you take a look at it, everybody? How to find minimum and maximum? Can you come back and talk to me just 1 or 2 minutes next time? Everybody should talk about how to find minimum and maximum, because that is fundamental. Okay. You can show one example, simple example, quadratic example. The first derivative is this. Second derivative, you need two conditions. First derivative equal to 0. Second derivative should be greater than 0. Second derivative value should be greater than 0 to find the minimum. For maximum, second derivative will be less than 0. Very simple condition. And Rajan, I understand now why you express some challenges and so on. My apologies, because I thought somehow you are an engineer. That was my mistake. But it's okay. As long as I absolutely believe in what I'm saying, that as long as you are curious, you want to learn, it will come to you. The beauty of mind is that, once you have a question, sincerely, if you ask a question, it will not rest until it finds answer.
Correct.
Right?
Yeah.
So because of that, I'm sure that's why I believe that I can teach these things for high school students. I really feel that way. So next time when you come, whoever can do it, you get extra points, extra star, right? Extra stars is coming. You may know you get extra stars. If you explain how you will find a simple example, show me, this is the function. There are lots of examples out there, right? Quadratic is fine. Take some interesting examples. And what is the problem with that? And I also want you to tell me what is the problem using that calculus method. Okay.
So, what is the question again? So I'll also go and look.
Show an example using derivatives. Show an example using. Please write it down. Using derivatives. Show an example. It can be a very simple function. How to find minimum value of a function or maximum value of a function. This is fundamental, Rajan. Even if it takes 1 week for you, you got to internalize this, because optimization is what's going on all of data science. If you look at our linear regression, what did we optimize? What did we optimize? Every solution is an optimization problem. What did we optimize? We optimized minimization of the sum of squares of errors. Right? We minimized sum of squares of errors. In the logistic regression, what did we optimize? Write it down at least now, because I wanted to recall this. Maximization of likelihood. That's what we did. Okay. So in the case of support vector machine, what are we optimizing it? We are optimizing maximizing the distance between the collection of points. Maximizing the margin, but within that equidistant line. Maximized margin, and within that the equidistance line. The point is, and the equidistance line, if you know the margin, equidistance line is basically the distance between the point and the line, isn't it? And it should be same on both sides. That is what the optimization is. So, but I'm not asking these are general statements, Rajan. I'm not asking, go and show example like this. No. Just take a small example. U curve, quadratic curve. It's called quadratic curve. U curve is called quadratic, right? So take a quadratic function. Show me how you will use derivatives to find maximum or minimum. Because you can be inverted U. Either way is, if it is inverted U, then it is maximum. If it is a regular U, it is the minimum point. How can you use? This is the question I have. This carries double points. Jeopardy, double points, double stars. Okay. So show an example that the derivatives can be used to find the minimum or maximum in a simple quadratic function. Everybody's good? You can show me, explain an example. If each one of you explains in next time, actually it is a great review. You will never forget. Remember, 6 times you repeat. It can be. I hope it is a different example. Don't bring the same example. Hopefully not. And who knows, right? The greatest example, if you see it in the internet, that may be the one you pick up, understand and explain, right? It's okay, but bring, hopefully we will have different examples. That's a great review. Shaktivel, you will be able to do that, right? Because you are an engineer. Easier for you. Right?
Yeah, sir.
No.
I done it before.
I'm sorry.
I done it before in my
you
college
done it
days.
before. Somewhere else, right? Not in our course.
No.
Yeah, so sure. Soumya, are you? Yes?
Yeah, I will be able to do. Yeah, I have done that before.
Excellent. Okay, Saranya, you have done it recently.
M4, sir.
Huh?
Fourth semester, max. M4, sir. I've done it.
M4 means?
I remember.
Math 4?
Max, sir. Fourth semester, max.
Oh, yeah. So you know it. Rakesh knows it. So after hearing all these things, Rajan, you will know it for sure. Okay? And you try to get also. But why do I spend so much time on this? It's so fundamental. This is going to be repeated again and again and again in every data science solution, in every AI solution. The algorithms are optimizing something always. That's the only way. So, okay. So what we are saying is, I gave you that if I want, I can find this distance, right? So if I'm going to, I given a point, support vector, and the line, I can find the distance like this in this form, using this form. This, you read this one, this line, you'll be fine. So here minimization is, and what we are saying is that this distance will be equivalent to this side also. Suppose this is support vector of the black points. This is another point here is support vector of the white points. Then that distance should also be equal. That's what we are saying. So the optimization is, it is the equal point, right? So that becomes the following mathematics. Okay, that becomes the following mathematics. That's what this problem is. You see this one? So what I am saying is, basically I am going to maximize. See, remember maximum margin? So that's what we are saying. Maximize 2 over W square. W square is the parameter, linear parameter values. W square refers to the L2 norm. L2 norm of the linear parameter values. A, B, C there. Those are the values there. W. Are you with me? A, B, C I showed you earlier, right? The distance between a point and line. A, B, Ax plus by plus c plus 0. That is what is inside this W vector here. Where is it? Sorry, handle is not moving. Okay. Inside this W, are you able to see this? What I'm saying? Inside this W, that's what this, right? And we, maximizing 2 parts because one of them is that distance, okay, and the other one is this below distance. Right? No, we should be maximizing that. Do you get the logic here? Working out all things coming together.
Why? So is there a possibility you could have 3 divided by W2?
No way. Because why happen to this part is, I'm saying this is one part, this is another part. Both should be, this is what the distance here I'm saying this. Because we can also say this vector should satisfy, this is +1, this is -1. That is the equation, right? The whole class is called -1 class. This whole class is called +1 class, right? I talked about that also. You did note them as +1 values, this note them as -1 values. So this line has to satisfy -1, this line has to satisfy +1, first and foremost. Because of that A plus B, AX0 plus BX0, that equation, right? That one becomes 1 here, and the denominator is basically that A, B, C value. So let me go back one more time and recall this one. This AX1, BY1 plus C becomes 1 or -1. So it's absolute value. So it is 1, right? And this one becomes the L2 norm type information here. That's a distance, right? Distance, square root of A square, B square. That's what it is. Okay, that's what this one is coming out to be. 2 over, because this is 1 over W, right? And then this is another 1 over W, so it becomes 2 over W. Good? Rakesh? So if somebody asks you, I don't think they will ask you, but you can say that, you now know it. So what is that? What are we maximizing in SVM? This is what you're maximizing. Raja? In linear regression, you are minimizing error sum of squares. Here you are maximizing this distance. That total distance is 2 over W. That W is coming from the support vector point, any one of the support vector point to its line. And this support vector point to the same line. So their distance should be equal. So it becomes 2 over W. And that has this structure. It is coming from this structure. Everybody's good? You will remember this, what I'm saying? So you know how to articulate. So now that you know, you can go and do whatever your programmatic or solutions. Very straightforward. But that is still only for non-overlapping points. Right? Raja, I'm coming to the question you raised. You kind of,
Yeah, sure, sir. But before that, so to the previous question you asked, right, whether it's 3 or 2 or 7 we spoke about, right? So there it is only 2 then, is it? It's not 3.
Yeah, it's only 2. I thought I answered that. The total
it's only
is
2, right?
3. Total is 3 support vectors. 1 on the other side, 2 on the one side.
But
Total
the vectors are only 2.
But one side it
support
is 2.
vectors.
Okay, let me go back one second. Hold on there.
So here support vector is only 2, right? Actually, yeah. This one or the one before.
Support vector is 2 for one side and another one for the other side. Totally 3 support vectors.
Okay. Because here have 2 points where the line is passing through, right? You mentioned some.
This example, are you talking about this
or something? No, the one before.
Okay.
So here there's a dotted line on either side of the gap, right? The gutter, or I think you said something, right? So the one below, we have 2 points, right, in the red set, right? That it's passing through, right? The dotted line is passing through. So this was the basis on which I said 3, right? But then
this
in
one,
the slide
this
later.
This one and this 2, 3. That's what I thought you said. Yes, right? This
correct,
one.
correct. Okay, but I said 3.
Correct.
But in the further slide where we were discussing, I thought we were talking about 2 by W squared or something, right? Where the argument was that there are only 2 support vectors actually.
Right. So the distance, I know what the question. I understood before, but I wanted you to explain. That doesn't matter. The distance from here to here or the distance from here to here is same because it's a parallel line. You see this one? That's how it will happen. Because of that, it doesn't matter. It's really the distance from any point, either this or this support vector here, is same to this line. Likewise, the distance between this line and this line is also same by the equidistance condition. So,
right. So,
even though there are 3, there are only your optimization is still the same thing. That's what happens. 2 divided by the norm square. That's called norm.
Yeah.
Yes.
And then the basis is that we will think it's only 2 support vectors. Is that how you look at it?
No, it doesn't matter. Eventually, the support vectors are those factors that are helping you to define the separator. Okay.
Okay.
Thank you. So, but the quantity, mathematical quantity is just those 2 divided by norm square. Mathematical quantity.
Okay.
All right. Okay. I understand that there is some little bit of clarification is there. Okay. That's because we are only optimizing the distance quantity. That is just 2 divided by norm W. Now W's are the weights of the equation. weights of the separating equation. It doesn't matter, maybe 10 points also, all are the same. But they are all support vectors. They are all defined as support vectors. Okay, any other question? Wonderful. Let's just, do you want to take 10 minutes now? We defined almost. Now, why don't I give you this final nonlinear separator equation? Then we do the remaining part, some exercise. So the question is, so this is what it is, right? I have come up to this and I explained all these things. Fundamentally, it is coming down to this equation. Just a second. I lost my arrow. Okay, here it is. There are some notations here, don't worry about it. It comes only by, it's like giving a name to a person. You cannot ask why that name is like that, right? So just, like that, this is the notation you be used to write an equation. Now, I can write this as, instead of saying maximizing W, listen very carefully. It's same as saying minimizing this. Agree? I switched it. Sometimes we say minimizing, sometimes maximizing. Right? Minimizing is what we like in general. Okay, because minimization, everything is minimization. Maximum likelihood we say, but that is actually because it's minimization of minus log likelihood becomes the maximization actually. Minimization of log likelihood becomes maximization of minus log likelihood. Right. All right. So so minimization is, this is basically the equation, the math, the algorithmic step is this. Minimizing this kind of expression subject to this condition. Remember that. In other words, these things should lie. These are the vectors, right? This vector, what are the support vector? For that vector, support vector, it will be equal. For all the non-support vector, it will be greater than this number. Again, I'm writing it in algebra, just to giving you a structure. Yeah. Somebody wants to say something? Now, what all I want to get your attention is, what happens when we have overlapping points here like this, right? This red line is inside here. This green is inside here, right? This kind of, but the support vector is, there is no way I can do any other way than, something that points out a line, which is to the left is supposed to be only green, but only one red is there. That's okay. And to the right, all support is supposed to be red, but we have one green. That's okay. Because there is no other way I can solve this problem. But within that condition, how do we find that one? We still have the same problem. Okay, these are errors, right? This epsilon. This is the 17th point. Okay, this is the 17th point, right? The 17th point error is this. That is an error component coming now. Earlier, I didn't have any errors. Remember that. Are you with me? These are errors and noises, right? Errors and noises are. So we are going to account for that errors and noise. This is the error here. This error is, it is supporting. This is not, we had in the previous case 0 error. We didn't have like errors like that, but we are going to account for these errors. In this case, there are 2 errors. 9 and epsilon 9. That's epsilon error 9. This 17th observation has this error. So as long as we take care of that, we solve the problem again mathematically. Agree? Okay. I had 2 nod, 3 nod, 3 nod. Okay. Rajan is bewildered. I know. Just hang in, Rajan. We are going to be for life connected on these principles. Okay. You don't have to know all these things, but for me, it gives me satisfaction that I'm able to explain this. And
Connected on support lines.
Huh?
Connected on support lines.
Don't worry about that. No. There are analysts and analytics managers. Remember that too. There are analysts and analytics managers. Analytics manager, they are not on support line. The analysts are support line, the analytics managers. Okay.
No, they are the margin lines supporter. Margin lines of
No. The analytics managers have their they keep the analysts sometimes on support line, because they are in need of supporting their management, right? They are responsible to to make sure that the algorithms are done, developed, applied, and so on. So let's not underestimate the importance of analytics managers. I know that. Okay. All right. So, but the analytics managers who know these things, and can ask better questions. Do you agree with me? That is my point. You can ask good questions. It comes down to really in life, it's really about asking good questions that will automatically lead to good answers. Good means something I cannot characterize now. That's a relevant, very focused point to unravel something. That is a good question. And if you ask that good question, it will be addressed. There is nobody can stop that, because otherwise it looks like stupid, right? The person who is being asked, either he has to accept, look, I don't know now, I will come back with an answer, or I know the answer here, because you cannot give a dumb answer. Because you as a manager, you know that something is not right. All right. So let's just fix this problem of errors, and then we solve the problem again. This is where it becomes a little bit more mathematical. So same thing, but it is not like this anymore. It is like this, less than or equal to 1 minus epsilon I. And this epsilon I is non-zero for 9 and 17. Correct, Raja? This is the only structure. This is what it is. Earlier we proved it. This is all we need. But now I'm saying we are modifying it. There are two parts to it. There's a cost attached to all these errors. Think very carefully. There's a cost attached to all these errors. And then this condition, this less than or equal to, should satisfy this condition. Everybody's good? Why? Because I am allowing, it should be strictly speaking less than or equal to 1, but I am allowing some errors. So it can be 0.7, that's what I'm saying. Here it cannot be 0.7. If the error is, let's say 0.3, then this is 0.7. We allow that. All boundary conditions should satisfy this. And if it is 0.7 and another one is let's say 0.3, one is let's say 0.5, then all points together should satisfy 0.5, because that is the smallest compared to 0.7 and 1. Everybody's good? That's all we are saying. Intuitively I'm trying to appeal to you. I think that is great enough. If we can come up to this, is great enough. But I also introduce a cost attached here. Look at this one. So as the errors increase, I will be more and more, penalizing. Right? I will be more and more penalizing. So there is something going on here, but nonetheless, it is, that's all to it. Mathematically, I can solve this problem. So you will see in the application, you will see the cost function coming into it in the application or program, you will see that. So we have to try it. It's a kind of hyperparameter. We don't know. We have to try different parameters. And whatever that gives you the right value for which the confusion matrix is good looking, we select that. Everybody's good? You see the strategy here. So C will become a parameter, hyperparameter, right? And then we solve the problem for SPM with hyperparameterization. Here, all these mathematics, how this is optimized, there's a mathematics behind all this, this derivatives or whatever it is, we do not worry about that. I don't want to go into that. This is good enough. You know all these things, you are good enough. So what is the managerial question here? You can say that now if somebody just gives you an answer without this hyperparameterization optimization, then you will ask the question, yeah, what happened to hyperparameter in this case? That's the kind of question we are talking about. That's where you connect with the problem.
What is this hyperparameter you're talking about?
Hyperparameter is a parameter we don't know. But you have to, computationally you can determine. Right? So here is the example. We are going to show that, but I will stop this here. These are two example, overlapping example, Raja. Overlapping example means I think Raja, right? But everybody, should listen to that because he asked that question initially, right? So, so here you can see that this is the value 1000. We need 1000 here. There's a high cost attached to it. There are many points here. Okay. There is, it's almost on the boundary. That's why you don't need to penalize that much. Too much a small error. Almost on the boundary. But here, little bit more on the boundary, so you attach more cost. but here points crossed between. Okay, so we attach more cost. So this we will find out in our computational way. That's what the hyperparameters are. Everybody's good? So when you come back, and then we use all this kappa, this and that, the same thing. Confusion matrix, F1, all those true positive, all those things, same thing. Everything is same. You are ready now to go to R? When you come back. 15 minutes. Thanks, everyone.
Recording, sir. Chat.
Okay, I recorded. What is that you're saying? Additional?
Yeah.
All right. Welcome back, everybody. Sami, are you there?
Yes, sir.
Good seeing your smiley face. Good. All right. Sami, are you there?
Yes,
Okay.
sir, I'm back.
Okay, good. All right. So I said at the end, it is still, even though I added the epsilon in the optimization and so on, it's still for linear separators only, not non-linear separators. Right? There is more to do. Come to that. But we will start right away. The nonlinear separator is, basically about kernel functions. I didn't go to kernel functions now. That's okay. Let's just, work out the solutions using R now, because in real life, that's what you are going to face. You will be given data. You have to find the separators. Okay. And so here is the example I want to share with you. So this is 1 second. So it is here. So I think if I click, it should come. Let me see. It's embedded here, I think. Oh, by the way, I want to show you. Look at this one. These are all the different data sets. Okay. Different data sets, right? Are you able to see what I'm showing you? Here it is. Okay. So the black dots are the performance of SVM, and in comparison to random forests are the bars. Random forest, you can put anything, right? Random forest, the boosted random forest and so on. But somebody analyzed it. It should be somewhere. I don't know where the reference is. I have to find this out. So in this case, we are talking about the AUC outperforms. In this case, the SVMs outperforming AUC almost all, except in these two cases. You see this one? Are you with me, everybody? The Lizuka and this PX Bhattacharjee. Okay.
Sir, what is this data set, sir?
This data set
is the gene selection.
Yeah, I
Gene selection.
have to get back to it. It's about some analysis of genes analysis, genetics analysis. I'll have to get back to the data set. I have to get back to the reference also. No, it's not here. I thought it's just good to show you, to get you the belief, the trust that here is an example, comparison example of SVM versus random forest, where almost all of the times, except the two, right? Almost all the times SVM was beating. So this is results with gene selection. This is without gene selection. I'm not giving you enough details. I'm more concerned about only at this time the algorithmic preference. SVM became very popular in the beginning when it won certain competitions, again for image classification, before the convolutional neural networks. Okay, before the convolutional neural networks, which is what the deep learning is, we are going to see. SVM was beating even in the image classifications, but eventually deep learning gotten over, now deep learning is the hot topic. We are going to see that next week onwards. So anyway, so let's go back to this, SVM hot study analysis. So one moment. Why it's not coming out? I want to exit this one. One moment, please. One moment. Stop sharing. Huh. I want to get out of this mode because I need to click on that. I need to click on this. It's not coming out. My PC sometimes can. Okay, it came out. Okay, let's do this one. I think I can just click on it. No. Okay, yes, it is working. Let's see. It should automatically open all. Oh no, it doesn't. It just gives me this one. So let me go back to. I should be able to open it here. It's not here already, so I will open it here. Open recent files. Open file. It's called SVM. Hot area analysis. Okay. So here is a hot area analysis. Okay. So this data set, I don't know whether I have given you this data set. So let me also send you this data set. Okay, right now.
Screen share ಇಲ್ಲ
Huh?
Screen share turn off ಆಯ್ತು.
Oh, I see. One minute. Oh, yeah, sorry. Yes. Oh, that's how I could use I could get out. No, okay. All right. Okay. So I'll send you both the program as well as the data. Okay. Let's see where the data is actually read from in the program. I have to go back to the program and find out. Oh, it is in the YAML. Okay, so that's fine. So I'll do data also, attach data also. So it is called hard study CSV. That's what the data set name is. So it should be here. Hard study CSV. CSV. Okay. Hard tidy CSV. Okay. Attach that too. I sent it to you, Supriya. Okay. Okay, let's run. So this is, everybody knows how, what I'm doing here, right? Any questions here? It's very straightforward, right? I'm read.csv. I'm reading the art tidy. After we read, we will find out what is there, okay, using structure. All right, so let's do that. Is it working? Yeah, that's fine. This part is not working. There's some problem here. Okay, I have to take this out. So I read the data, so let's see the structure. So there are 14 variables here, 300 observations are there, 14 variables. And in order to get the same results, you should set some seed, right? Set seed, some number you give. I just gave 30, 33, but you can do. So that will set all, if you repeat this analysis with this seed, you will get the same answer. That's the idea. So now I'm taking I need carrot. So library carrot is here. I should have run that. I need carrot for this. This is done from carrot package. Carrot package has nearly 100 plus algorithms. Okay. If one package you have to learn for machine learning, this is one of them. Everybody got it? In R. So there is a create data partition, and then it gives me which variable to use, and then I'm saying 70% you put it in training, 30% you put it in testing, and then you don't create it as a list. Okay, just to keep it as a data frame. So that's what it is doing. I run that. So in train gives me the indices. So I use that indices to select the art df data, which is already read. And then testing is minus of that. That's what it means. It's done. Minus testing is also automatically done. Okay. So now I'm going to check the dimensions. It will tell me how many rows and columns are there for each. So it says here at the bottom, here, 210 went into 210 rows went into training, 90 rows went into testing. Summary, let's do a little bit of summary quickly. And this is what is happening for each of the variables. It's all very straightforward stuff, right? Now, I want to consider 14 as the variable. Let's do the 14. What is going on with 14? 14 is also 0 or 1 only. Okay, so it's not multiple classes. So we want to do the training 14th variable as a factor. You have to define it as a factor. If it's a numeric, it won't work. Okay, it has to be a factor. So let's do that. And then we do the train control. Do you remember that train control, grid control, all those things, right? You have to do that. So here's the interesting variation of what I did before. It's k is equal to 3, but we are going to repeat that 10 times, which is a validation. K is equal to 3, and we are repeating that 10 times. What does that mean, you think? K is equal to 3 fixes us the 1/3, 1/3, 1/3. But what 1/3 we put is also random, isn't it? You understand what I'm saying, everybody? What 1/3 goes also is kind of random. Am I making sense to you? It's a kind of random too, because if I take another 1/3, 1/3, it may not be the same. In all probability, it won't be same, I can tell you. So what if the first 1/3, 1/3 you take are kind of some biased, biased split. So in order to avoid that, you do this repetition 10 times. That's what. See, data science in the modern world is highly computationally intensive work. That's what is happening in data science. So what we are saying, you do the k is equal to 3. That itself is a repetition 3 times, right? 3 times you are modeling. That's what it means. But in order to avoid even possible biases in the selection of that first cut, 3 cuts, you are repeating that 10 times, 10 different k is equal to 3. That's what this means. Everybody's good? Yes? I resetting this, this part. Again, there's a set seed. This is after the sample is set. Okay, after the sample is set, I'm getting a new set seed. You don't need it. If you don't want it, that's also fine. I can take it out. Now I use this train is a function. That's what is called. A train is a function, but I'm going to call it as SVM linear. The method is SVM linear. Train control is, this is the control that's coming from here. Pre-process center scale. That is another thing I want to talk to you. Tune length is 10. So data is training. That's what is given here already, which is defined here. Training is the data set. Testing is the testing data set. We are going to use the training data set. Repeated CV. The method is repeated CV in the train control. And then what method we are using here is the SVM linear. Pre-processing. So oftentimes you do want to do this pre-process. That means you standardize the data. Sometimes people say normalizing it, standardizing it. Mistakenly this way also harmonizing it. That's not harmonizing it. Standardizing center is better. Standardizing the data is better. Data columns is better. So that all variables are comparable. Otherwise, you remember that the age can be 2-digit, income could be 5-digit, right? That's not good if you want to compare the impact of variables. So once it is done, when I call this object, it's going to print me the contents of what is stored in that. Shall we do it? Ready so far? Everybody? Pretty quiet. Okay.
Yes,
Yes,
we
sir.
can.
Right.
Yes, sir. Yes.
Yes, sir.
Rajan.
Yes, sir.
Yeah. All right, so let's do this. Oh, well, I didn't do all these things. Maybe I should have done it. Okay, sorry. And then comes this, right? I can do this one. SVM linear. Why is that it's not working? Control Enter. Okay, it is running. It ran only that part. It's still running, okay? Oh, it requires a package is needed for this model and is not installed. What is called kernlab. So I'm going to say in the control, below you let say yes or no. It is asking yes or no. Do you want me to install or not? And that is coming in the console panel. It is here noted, but it's coming here. I can give selection only here. So I say yes. If it's needed, of course, I want to install. Sometimes it can take, remember, if it is a long, a lot of data, it can take more time too. Okay, error. Oh, I see another package is needed. So let me go back because I know that package is here. Let me call that package E1071. Oh, not this. This package should be there. It's not there, so I have to install that also. Okay. E. Install that. And then I will install kernlab. Install kernlab, okay. That's okay, fine. Restarting on. Kernlab, come on, one more time. Oh, it is retrieving package installation, okay. It is done, maybe 1 second. That's the reason why it was saying restart. 1 moment. Yes, it's here. Okay, so that's done. Let's redo it. Redo it one more time. I'm doing the whole thing now. Oh, what is this? Could not find function train. I thought I did library. Caret. I thought library caret is there. Check again here. Oh, caret is not in the library. That's the reason. Okay. That's the only reason. That could only be the reason, right? So let me do one more time separately. That alone. I'm doing it. SVM linear. Not bad. Okay, finished. Because it's a small data set. Okay. Then I want to print that. So here is the printed. Accuracy is 76%, kappa is 53%. It's a 10-fold repeated 3 times. Okay. The tuning parameter C was held constant at values 1. So it optimized, okay, itself. So tuning parameter is that. But if you want to try with varying cost, here is the loop grid. You are going to set the grid. Are you with me, everybody? Very important. Now I just jumped quickly. Sharanya, do you see what I'm saying?
Yes, sir.
Excellent.
Yes, sir.
Rakesh, Soumya. So it came with 1,
Yeah,
but
yes, sir.
I'm sorry, go ahead, repeat. Soumya.
No, I said yes, sir.
Excellent. Raja, Rajan, Goshali, Shaktivel.
Yes, sir.
Good. Okay. So I'm kind of going to go with these cost functions. It said for me 1. So maybe I'm thinking a little bit less above, maybe, make you a little bit better answer, right? So I set that value in order to get this again. Remember that you can set these things. This set C to get back to the same answer if you want to repeat. Okay, that is done. And then I'm just checking grid values. Grid values are this. And then now I'm going to do the over the tune grid. Okay. Now I'm going to do the over the tune grid. It's running. It will take a little bit more time because it is working on and it is done. Okay. It's working on, for various variations of C values. So here is the answer. So based on that, which one will you consider? One is 0.767735. 0.75 is also same thing. The rest of them are also the same thing. Okay, but you can you can use additionally kappa. So kappa is the same thing. Either one is fine. So and the system gave us this way. Are you with me, guys? But
Yes, sir.
in this case, it is saying that the final value used for the model is C is equal to 0.75. It just took whatever the one that came out to be the equally best. That's all. There is no reason here. Less cost is attached, okay, which is 0.75 for each observation. So instead of so this is where the what is that? The kernel functions come into play. I'm going to run this also, but I will explain the kernel function, importance of kernel functions here. How mathematically we think. We'll come back to that. But there are a few kernel functions. Why don't I go there and just finish this? Okay, let's see kernel functions.
Why did it select 0.75 actually? I thought.
Yeah, it just selected the first one. That's all. They all have the same, right? The results turned out to be
Yeah,
same.
but the kappa value was lesser for 0.75.
Yeah, that is
that the reason?
that is strange. You're right. Yeah, I don't know whether how many decimals they use. So it is happening at the 4th decimal. This is the difference between this and this is 0.00003. Because -3 is minus 0.403. I'm not sure where they are using the decimal number of points. I don't know. Okay, but I'll also do a little bit of research why they should go after this one. Okay, I think it is just taking the lowest cost attached to it. Okay. So let me go back to this, the kernel functions, right? Because I'm going to show the same example with the kernel, what is called the radial basis function kernel. Okay, radial basis function kernel. We'll use that in this example. But what we are saying is that I told you earlier that if there are non-linearly separable, you can find a function called kernel function, which is represented as phi, okay, that transforms all these points to a higher dimension. In that higher dimension, it's a 2-dimension becomes a 3-dimension. This is called feature space. This is called input space. Remember that. Remember these 2 keywords, everybody. Okay, because this can be a good way of expressing yourself. When you're talking about the kernels, because the kernels are functions that transforms the input data points, called input data points coming from the input space, into what is called the feature space, because that's where the modeling is happening. So that's called the feature space, and in the higher, it transforms the input data space into higher dimensional feature space. Within that, they are linearly separable. That is what the kernel function trick is. Okay, kernel function idea is. So what is that function? Some kernel functions are commonly known already. Okay, and those are, I'm going to talk to you about those kernel functions. Here are the 3 popular kernel functions. Okay, one is the quadratic function. So the quadratic function, what it says is, basically you take the vectors, right? The data, the vectors, and the vectors, whatever the vectors you have, you create this kind of expression, right? 1 plus the cross product terms. That's what it is, cross product terms. Okay, the cross product terms, and square it. This is cross product term plus 1. That's kind of bias that commonly referred to. Either this or this is, it might work. So square it. So this is a quadratic function. This is a quadratic expression. This is what happens in quadratic expression. Instead of quadratic, you can have a polynomial function. This is quadratic itself, a polynomial function, but with degree 2. But it could be very arbitrary degree. Okay, polynomial function degree d. Okay, so this is really should be d. Why? Yeah, it should be. It's a polynomial with degree d. Okay, that is the second popular. The third one is dr gamma. So the third one is what is called the radial basis function. Okay, forget about the complex names here. Radial refers to round. That you should be able to remember. Radial refers to round, right? So this is a kind of normal distribution also. If you look at it, if you remember normal distribution, let's take a normal distribution function in 3 dimensions. You can contain the observation as a circular points, right? One second, I'm going to show it to you. Whether it is 2-dimensional or 3-dimension, the symmetric circular will work there, right? Symmetric circular, is symmetric. That's why it is called symmetric, right? So if you look at the images, you can take anything you want. Let's take this one. What is the normal distribution? Or this one also. Okay. So this is equally, a circle kind of thing contains on both sides, left and right. Circle kind of things contains equally well. A circle contains observations equally well on the left side and right side, centered around its center. Okay, around its center. It could be this circle, or this circle, right? So radial basis function, the normal distribution has this. I'm not sure whether you know this or not, whether you can recall or not. So let's look at the normal distribution. Again, one more image where I want to show you the expression, right? The expression, mathematical expression is this. I'm going to show it to you here, right? The mathematical expression is this. So you see this one, exponential, forget about this constant here, exponential of this one, right? This is the square, okay, divided by some constant again. Forget about all these things. And this This constant, remove this constant, you can keep this one. Remove this constant, remove this constant. This part is the radial basis type function. Are you with me? I mean, in terms of logically, am I appealing to you? This is radial basis, radial type function. That is, the circular, because of symmetry, it can circularly, identify this part alone, this part alone, this part alone by a circular projection here. Are you with me? By a circular projection here, equally on left side and right side, by it gets a circular projection here. So its three-dimensional version is it is containing all the points here. And if I say anything inside, above, anything outside is below. Am I making sense? Some intuitive appeal I am making, right, Rakesh? Gaushali, Raja, am I making some sense there? Okay, that is called algebraically that part is called radial basis function. That's all I'm saying. Okay, so we need a name, so that's why I'm expressing that now. Let me go back to that expression. One second. Let me go back to this expression. So this is what it is. Norm. Norm is same as that. That x minus that center z square, right? X minus mu square. That is the kind of point. This is basically centered around z. Okay. So these are the three kernel functions that we will use, commonly we use. And if I use that, what we are saying here is, if I buy into that kind of understanding, I'm saying I'm going to use a nonlinear separator now, okay? But this time, nonlinear separator is defined by the kernel basis function called radial basis function, kernel function called radial basis function. So the method is called SVM radial. Now R is uppercase, you have to use that. If you call this, it automatically checks out, is there any nonlinear separation that needs to be fixed, and whether that is better. Okay, so that's what it is. Everything else is same. Is everybody good so far? So instead of using regular observation, I'm going to use a kernel transformation into transfer it to the feature space and apply the SVM method in the feature space. Samya. Okay, I mean, I understand, it's kind of coming, a lot of things are coming, but, I hope if you review this, you'll be fine, I feel. Many times, you may have to review 2 times, or maybe 4 times, or maybe 8 times. But if you review it, it will come to you. So, hello, Rajan. Are you there? Okay. All right. So, so calling this is very straightforward, but you have to understand why we do that. That is my point. Okay. Now, once I run this, let me run this one first. I have to set the grid. So this time cost is similar cost, but I'm using radial. So it is happening. The SVM is built. SVM is built with in the feature space with these cost functions. It's not using in the regular observation. Okay, remember that. One part. Why? I don't know why it is taking time. I thought I did everything else. Okay. So all right, maybe I should work on like this. Then it will solve all the problem. Okay, it is working, and it will do everything now. It will plot, including the SVM radial for me. So in the plot, okay. So here is the answer. Accuracy is in what right now? Accuracy is 87.78. Before that, 76. Are you with me, guys? Are you able to see what I'm talking? Kappa is also 0.5.
Yes, sir.
So this has done a much better job. So this is the control. This is the the output values. These are the so it is plotting me for various sigma values. Here it is actually sigma is the one that is used 0.01. So sigma is this one. Okay, sigma is this, C is this. So for various cost for each of these sigmas, right? And which is the accuracy, which accuracy is achieved in the repeated cross validation better? The 0.015 sigma is another hyperparameter. In this one, I will tell you what it is, because we are using the radial basis function. Radial basis function, remember, it has a sigma. I don't know whether I kind of highlighted that or not. So let me go back to that. This one, no, here. So this one, sigma, in this case, 1 over sigma is what is gamma here, basically. Okay, so you can call it as gamma also, that's fine. But it's called sigma there. But the relationship between sigma and gamma are inverse, okay? Inverse. 1 over sigma is here, what we have sigma. Instead of 1 over sigma, similar to normal distribution, here it has gamma. Is everybody good? It looks like a lot of variations I'm talking about. But just hang in there. Just hang in there and review this. And I connected that to every sigma here and then every cost here. And finally, it looks like sigma 0.015 is the winner. Uniformly, it beats all the other sigma values. That's also another hyperparameter, cost and sigma. Because the sigma is coming, cost is coming because of the overlapping of the observation, sigma is coming because of the kernel function transformation that we applied. Okay, and that kernel function has the parameter sigma, which is the inverse of gamma. Okay. So here sigma is I think I have a little bit careful about this definitions here, because he's plotting it as sigma. Okay, what we gave as sigma, and I'm telling you that it is sometimes it's also called gamma, right? Sometimes it's called sigma, sometimes gamma, and so on. But they have still a relationship. Just be watchful. But you just use only sigma in the case of R caret package. Okay. So you have solved this problem using kernel function, radial basis function, because you remember the very interesting thing I'm going to tell you. You can make radial basis function so small. Each point will be a circular point and it will be predicting correctly. Are you with me? Each radial basis function will be so small it can contain one observation. In other words, however complex the observations are, the radial basis function will solve the problem for 100%. But it may not work out in the test data set. Remember that. So you can get a perfect radial basis function based solution. But it doesn't matter. So you have to, that's where the validation matters, right? Validate, train, test, train, validate, train, validate, train, and then that should be representative of the best model for the test also, isn't it? So you cannot simply take, when you're talking about a small radial basis function, you're talking about a huge, huge sigma or very small gamma. Are you with me? Because they are inversely related, very small gamma. For a small gamma, I'll get for every point I can contain them with a circle. Radial basis functions are containing them with a circle, basically. Containing them with a circle. Okay. Are you with me, everybody? Okay. Good. So it did win the solution. So they are very powerful. If you use the kernels, it can solve a lot of problems. However complex it is, it can solve the problem. In fact, it can solve the problem so well, so good, you are more likely to overfit. Because every observation can be contained within a circle or a sphere in multi-dimension. Are you with me? Shaktivel, am I making sense? Am I making
Yes, sir.
sense? Soumya, Sharanya. You have to
Yes,
review.
sir.
Believe me, but I have given you a lot of details here. You have to review. If you review, you can go and repeat this in your job. This codes you can repeat it in your job. What else you need? That's all you need, right? You know how to do, why SVM matters, why SVM works, what are we doing there, and then what code will support that. You know everything. You can do today you can take this and use this in your problem, in your office. Like this, whatever I teach you, everything you can take it and use it today. As and when I teach you, you can take it and use it in your job. Any questions?
So this is
Okay. So let's see.
so I have one question.
Confusion matrix. Wait, confusion matrix also I plotted, right? I created. This is the confusion. Yes. Okay. Go ahead.
Yeah, this is okay. So while talking about kernel transformation in the beginning of the class, you said something about padding, right?
Kernel functions are padding. No, the that's
Padding
what
the predicted values.
You want me to show that one? Let me. I think that asked somebody else has asked. So go ahead with your question. I don't know whether that's what you're talking about. Go ahead with that question.
No. You said padding, like adding the predicted values to the current values.
Here is that.
That is kernel.
I'm going to show it to you now.
No, not.
Okay.
Okay.
Just hang in there whether it solves the problem. Let's see. The Raja also asked.
Okay. Sure.
So here each data point is like this. You cannot solve this by a linear separator, right? If I put this, it has these errors. If I put this, it has these errors. Linear separator means it can be only perpendicular, right? That's it. That's understood. So these are input values. Now we are going to transfer it to the feature values. These are input values. Even though both look like two-dimensional, really this is the one-dimensional data. And this Y is the class belonging to, Y is the class here. Y is a class? I don't know. It's just not even Y. This is what the data is, X. Okay. But we are making it in two-dimensional data. So higher dimension. With the kernel, the feature space will always be in a higher dimension. Okay. That is why that is how we are able to, create linear separators. So
yes, sir. This I understood. The transformation is clear.
No,
so
why?
This is what is happening in the program, right?
I'm sorry. Go ahead. What is that you're saying? Go ahead.
By kernel transformation, we achieve this. This is what is happening in the program, right?
Yes. So here is
because we were telling about adding. Yeah.
So this is what they're adding. This, adding or padding, whatever I said, right? So this is what your original input is x1, but the features are x1 and x1 square. That's my point. That's you padded that x1 square. Added. Right? Added x1 square. So originally is only x1. No, I don't need it looks like a minus. It's not minus. Okay. You just, I said this is maybe colon is better. One feature x1. But now input has only one. But the kernel, in the kernel space, we have x1 square. Why it's a kernel, you can see again. Now the features are x1 square, x2 square, 2 times x1, x2. That is the total collection of features. Okay. That is the total collection of features. Now each one is called now z1, z2, z3. The kernel function is that it maps x1, x2 to 3-dimensional data points. Okay, I would rather say this as this should be x2. Okay. Why is that? I'm not able to edit this. Okay, I will edit this one and show it to you later. The main point here is that now the original data are in x1 point values, right? x1 and x2. That's why I know it has to be x2. It's not y. I'm not able to change. Okay. It should be x2. One moment, please. This should be x1. This is the original data points, right? In x1, x2. But I transformed that in this way in 3-dimensional x1, z1, z2, z3, where z1 refers to x1, z2 refers to x2, z3 refers to square root of x1, x2. and kernel functions have to satisfy some properties. Not every function can become kernel. Okay, there are some properties, and there are some, we don't have to go into that. And what that, according to this property, if we take an inner product of these two vectors, inner product of these two vectors has to satisfy some conditions. Okay, and that it will satisfy that condition. The inner product will satisfy that, what is called the mode conditions. Okay, modes condition. So we don't have to get into that, but this one will satisfy. My main point is, it was x1, x2, but now I made it into x1, x2 to square root of x1, x2. This is what the added variable is. Are you with me now? And that makes it into a three-dimensional point. Are you with me?
Yes.
And in that three-dimensional point, this becomes, like this. It will become all, circular in this one. There is some notation problems here that now I will have to correct this. I'm not really, I have to correct the typos here. Okay, just take it to visually that these are the points that are there, but I'm making it into x1, x2 spaces like this. But three-dimensional space means there is a dimension here. If this is z1, z2, and there is a dimension here also coming out this way in that direction. Okay, the third dimension, that is a z3. And in that dimension, it's a kind of elevated points. These zeros, the red are elevated points. And this is the line. This circle is the plane that cuts it in such a way that all the above are red points, below are green points, so we get the separator. And this is what is happening. This is not what is happening. Okay, 1 second. I think that your question is, in the computational part, in the R, is this what is happening? Similar transformation is happening. This is what is called the this is a polynomial transformation. Okay, but what we are talking about is the radial basis transformation. Are you with me? The polynomial is easy to show for me, but what we are talking about in the R program, the R program is a radial basis function we are talking about, because I'm explicitly asking for SVM radial. Are you with me now?
Yes, sir.
I answered only what is meant by adding a variable. In the case of, it becomes easier for me to show it in the polynomial case. Are you with me?
In the beginning of the yes, sir.
Sir, so we use the SVM radial method, right? So basically, I think what you are saying is, we are doing this transformation, the kernel transformation, where we are taking it to a three-dimensional model. Okay, and bringing the
three-dimensional features.
Three-dimensional features where the data is actually coming in a radial, right, within the normal distribution or something, where you have it
usually circular, yeah, usually
circular, yeah, that's radial, right? So okay, so but is it possible to at least see what are those points or something from this data from SVM radial?
Yeah. You mean if you plot this
or using some function.
Yes.
Like the mean, median, mode, and all that we do, right, for the summary and all. So like that, is there something that we can use as a function?
The plot will tell you which are all contained, which part of the points are contained within a certain circle and so on. Because these circles are going to be all over, right? Okay. So this is what it will be like. The extreme case, I'm going to show it to you as an example. It's not really about mean, median, mode, but it's a question of how do we separate, right?
Example.
Yeah. I understand your question. Your thinking, I understand, but it's really more about how do we contain them within. Look at this one. So what
like
we are
here
saying,
we have root of 2 x1 x2 or something, right? So
so here
in the third dimension.
Here, let take a look at this one, and then I will clear out your question. So this is a multidimensional curved space. That's what it means. These are all the points which are red points outside this circle area, or let's say green points, right? These are within, and then again, these are all within this circle. There are red points again. Outside the circle is green points. So you can see wherever these circles are coming, above that are all red points, below that are green points. But it is able to separate it out. This one plane cuts all these things at these points and it separates it out. That's the point, right? That's what you're saying. And these things are all, each one is managed by the radial basis function in such a way that this separation occurs. Okay, now you ask me the question.
Yeah, question is there a way to see what is that new variable or the transformation that is added, right? We talk about this Z3 or something, right? X1, X2,
I understood. Okay, so let me go to, I think I have to show you a plot of basic data. 1 second. Of some data analysis, right? If I can show that, you will be fine. So here is one example.
But if it is not necessary, then we can just skip it, sir. I just
no. It's all everything adds for more belief, right? More credibility, right? So every little thing that is a question, as much as possible, I want to address that. So here is an example. I'll tell you. This was actually solved also. This is after a while, it is actually a radial basis function. Gamma is equal to 100. I don't know whether you can see that. Radial basis is actually a problem solved by, it's an example from Stanford University. These are the data points in the transform. This is the original data points, not the transform data point, right? This is the original data points. This is one axis x1 value, this is x2 values, let's say. These are the original data points. But you can see that it's perfectly, almost perfectly maybe, right? Almost perfectly created this line separator in this nonlinear space of points, red and green points. This separation actually is a solution coming from the radial basis function. Okay. And I have a code for this. I have to pull out that. It's somewhere there. I don't have it right now. I have it. I know. Because I have presented this in a different class a couple of years back. Okay. So why don't I come back with this definition? Will this satisfy that? No, I will tell you all the points, right? I will tell you these original points. I can also tell you, I think it is, I can tell you the point. They give you the list of points on the third dimension also. Are you with me? Is that what will help you?
Yeah, this is actually still in 2 dimensions, right?
It is the original data
not
point.
a transformed.
Yeah, it's original data points, but the curves are attained by the radial basis. These curves are attained by radial basis function. That's what I'm saying. So you might wonder, one side question is, you might wonder, sorry, you said all circles will come, but here it's not circle. But that's not the point. The point is, it depends on, some points are at a higher level, some points are at a lower level. But when you cut it by a plane, combined with all the radial basis function, see that it's called basis function. That means, what is called basis means these are the kernels. These generates the whole space. Okay, so there are multiple kernels that generates the whole space of data points, right? And all those kernels, when you combine together, this is the shape that you get. You know what I'm saying? Which in the feature space, it's a linear separator. On a higher dimension, it's a linear separator. But in the projected space, it will look like this line. Okay. So the main point here is these are actually printed in the original data space. But the solution is shown in terms of this curve using this solution coming from gamma is equal to 100 from the projection of the 3 dimension into the 2 dimension. From the projection of the 3 dimension. So there is a code. I mean, I have the codes for this also. I will send that to you. But I'm not sure whether that's what is bothering you. Go ahead, Raja.
No, that's fine, sir. Actually, I was trying to understand if there is the transformed values, right? If we can see that as in R, right? Do we have that?
The transformed values, I think, let me see whether I think, we should be able to see, but I had to go into the program, right? I have to go into the program, and then somewhere it is creating this. This procedure is creating the data set, right?
Okay. Okay. No, that's fine. I think
Yeah,
we can
I have
move
to go
forward.
into the program inside this train package and then see. I'm not even sure whether, not this one, this SVM here, okay? Let me see whether SVM linear grid, no, this is not linear, still linear. I'm talking about this. Let me see whether the list, so the one thing you can always do is now go back and see the list of, the object SVM radial, okay? Maybe it has, I don't know, okay? At this time, I'm exploring X levels, Y limits. So it must be here, I believe. Call, coefficient names, best tune, control, dots, final model. So let me go back to this, and see whether I can get, predicted is here, model type, model info metric, pre-process. So let me see pre-process. That is also an object, okay? BC, YJ, ET, range, rotation, method, mean. Big imp, median, data. Let's see whether data is the issue there. But this may be the raw data. See, that's what it is, I feel, okay? Let me see. My key is stuck now. Let's see whether I can just print everything. It's not working. Sometimes I get into, it says null. Data is null. I don't know. Let's see one more time. Okay. It says null. I don't know what happens, why it shows null. Okay, it shows null. Training data is also, it's limited data. It's not the transform data as far as I see. I thought pre-process will be the one. Not that. Resample. So we can pull out, but we have to go into the intermediate step. If it is not here, then we have to look into the program itself.
That's fine, sir. I think we'll move forward.
Okay. But it's a good question, because I really want to see, because I know all these mathematics is okay. All right, I trust, but I want to touch and feel the data, right? That's a good point. I think it would be a good way to explore also. One second. So these are the results. What are the results? Oh, it contains only sigma, C accuracy, kappa, accuracy, standard deviation, kappa, standard deviation, and so on. So let's explore this. How about that? It's a good question. Why don't we pursue this? Can you do a little bit of research on your side while I will also do some? Raja?
Yeah.
That would be
Yes.
ideal, because I know it's all good, ways of getting more and more familiar with the procedure, ideas, and so on. What you asked. It's a valid question, okay? It requires some work. All right, so let me take a look at that one for you and others. Any other question? Rakesh, you asked some question. I thought you were raising that. I thought I heard your voice.
No, sir. No. Actually, what I wanted to ask was, you said we will be adding predicted values into the, the original values, right? When we are talking about kernel transformation in the beginning.
No. Kernel transformation, not adding the predicted values. It is transforming it into a higher dimension space. The original dimension is transformed to higher dimension space. In the higher dimension space, linear line or linear plane will separate the classes. That is the idea.
Okay, because maybe I misheard in the beginning, because I heard like padding is adding predicted values is padding like that.
No, adding new
I
variables. Adding new variables.
Okay.
I don't know padding is, I just said padding, but no. Probably adding is as simple as that. Let's use the word adding. But the point is, it's adding new variables. New variables from the existing input variables. Some new additional transforms. Okay, that's all. Okay. Any other questions?
Okay.
Any other questions? Gaushali? All right. Soumya? Sharanya?
No, sir.
So this is a
No,
very
sir.
powerful method. SVM is a very powerful method. I'm going to now go back to the beginning. I said it's powerful for few reasons. One of them, can you recall one reason? Extremely powerful. And Gaushali, you were kind of showed some interesting, expression when I said that. That at that time, when I said the answer there, can you recall? I can't hear you.
Sir, it makes it linearly separable.
SVM is linearly separable always, right? Eventually, it's linearly separable always. That's one powerful method. Yes, absolutely, I agree. All solutions are linearly.
It's more powerful for image classification.
It has one image classification. Actually, it was used for handwriting. It won in the handwriting competition. I remember that. That's okay. It wins in competition. That's what you want to say. That's fine. That's good. Anything else? One very, very important. Very important.
Dimension,
Huh?
higher dimension. Higher dimension.
No, higher dimension is already we talked about it because it's linearly separate. It connected to the linearly separable issue, right? The solution depends only on the support vectors. It doesn't depend on rest of the points. Solution depends only on the support vectors. And the algorithm, mathematical and computational algorithm, somehow cranks this out for us. And that somehow is a little bit hidden, a little bit confusing. We are not able to touch and feel every little bit part of that, like what Raja was saying. Can I see that point? In the higher dimensional space, what are the points for the data that we see in the heart study? Okay, but nonetheless, the beauty of mathematics, algorithmic thinking of humans, it's not the machine knows all these things. It's all hype. Machine doesn't know. We push it to the machine and we claim machine knows it. No, we are very smart. We push it to the machine, but we like to know. We like to say that machine knows. That is, it's a little bit of hype. We like that. Okay, but it's an enormous amount of human thinking goes into it. But it figures that, and eventually it gives the solutions, and it's perfect. It's mathematically correct, credible, computationally correct, credible, intuitively correct, credible. Does machine know all this thing? No. But we like to say machine learning is machine learned it. This is a conversation between you and me. If you go and tell, probably they'll think that you are a big fuss. So it needs only the support vector, nothing else. That is my point. And it finds the support vectors. The algorithmic step finds the support vectors. Okay. Now, any other question? Rajan? Soumya? Sharanya?
Will you be going over this?
No, sir.
One moment, one person at a time. Rajan first. Go ahead. He said something, question.
No, will you be going over this again, like a refresher or something?
Can you listen to this recorded version and pick up the areas and then ask questions? That's better because it is there, already there for you. It will be there. Everybody, I'm telling everybody to listen to it and then ask the question. It's very, very, very important to listen to it. Okay? Is it a good idea? How about Rakesh? Samya? One small thing that Raja asked, I'll come back to that. Somehow I'll try to print that, the values of the support vectors and how to get support vectors from the computations, right? And also how do we get the Z1, Z2, Z3, all those things. Is everybody good? I'm just looking at the clock. By the way, just a quick check. You all get tired with 3 hours of listening to me? You think? I don't know, is it too much? A lot? I want you to be honest.
Yes, sir.
It's a lot, too much. Huh? No, it's lot is different from too much. Not able to handle. Or
No, not like
So
that.
PA1, PA2 was fine. This one is a little bit exhausting.
exhausting. Okay. But
Sir, today
is it
was very-
exhausting enough that you are kind of frustrated somewhere, teetering on frustration?
No, not
at
frustrated.
all. Not frustrated.
No, not
It's
frustrated.
hard, I know, but what impresses me is that when I see people like you who are so interested in the subject, come and commit your time. You have so many things to do. You have so many things to do in life which you can do, but you prefer to come and sit here and listen. And it is demanding a lot. There are a lot of areas of uncertainty, but still you accept some of them. Yeah, okay. You are telling me I buy into it today. I'll check it out tomorrow. But today I will okay. I'm okay with that. A lot of issues are going in there. You are kind of you are packaging them, putting it in the boxes. One day I will open it and then verify what you said, true or not, right? But then you buy into it, spend time. It's a lot of responsibility, a lot of, a lot of work, a lot of commitment. And I appreciate that, but I just want to hear whether it is frustrating you, it's too much. I know we worry about that as teachers, right? How much can go? Keep on putting indigestion. Huh? What?
Here we are learning new things and it is more depth into it in ML. So it is a little bit difficult. So once we practice, it will get it.
So that is important. You have to practice, you have to think about it. Remember, I have a lot of experience to claim certain things and so on, believe in more than you, but you can get there too. The question will always come to the following: why the heck I should, commit my life to this science? There are other things to do. I can be a great singer. I can be a great sportsman. They are fun. A lot more fun, I think. Right? A singer, I think, is having fun time. And everybody pays for him. For his joy, everybody pays the money. A sportsman also like that, right? So that question will always be there. But that is already past, I know. I know that you made the decision. You passed that. But reality now strikes, right? After all these times. Gee, I wish I knew this. I hope you don't get into that situation. Review, practice, you'll be fine. You'll know more than others. That's the first point. It's not that you know everything in life. You will know more than others who are in the group, in your group. You are the lead. What is that they call the hippo, right? You are the hippo. That's all matters. Right? You have to know more than others in a consistent way, not in a just frivolous way. In a consistent, relevant way. You know more than others. So you can go and explore, you can guide others. So don't get frustrated. I know it's demanding a lot of stuff, especially this course maybe, because it opens up new types of mathematics, new types of approaches, and you never heard of these things, some of these things. Regression, you heard of it ever since, I don't know, right? So many courses you heard of that. So hang in there, practice, be sincere to your commitment you've made. You'll be fine. 3 hours, I appreciate your patience. Any other question? Rajan? Okay. Sharanya?
No, sir.
Practice. That's all I'm asking. Okay. Thanks a lot, everybody. Have a great rest of the week. New week next week. Bye.
Thank you, sir.
Yes, thank you, sir.
Bye.
Thank you, sir. Thank you.
Thank you, sir.
Bye, Sharanya.
Bye, sir. Thank you, sir.
Thank you. Bye.
Bye. Bye. Bye.
I'll call you. Bye.